Welcome back, students. Today we will see the solution of a rectangular waveguide in a rectangular coordinate system. So as you can see from the figure that the rectangular waveguide is drawn in a rectangular coordinate systems where the width of the rectangular waveguide is maximum up to A and height of the rectangular waveguide is in a maximum is B, and the wave propagation is in a minus Z directions. So our objective here is to find out the solution of the each wave electric field intensity and magnetic field intensity wave equations. So solution can be either in a time domain or frequency domain for the each E and H wave. So but we will try to find out the E and H wave equation in a frequency domain. So I can write the E and H wave equations in frequency domain as the del square E, that is equal to gamma square E, and magnetic field intensity equations can be written as del square H, that is equal to gamma square H, where we know this gamma is nothing but the propagation constant, and that is equal to the under root of square root of the j omega mu in bracket sigma plus j omega epsilon, where mu and the epsilons are the permeability and the permittivity respectively, while this sigma is the conductivity of the medium, while the omega is nothing but the operating frequency, angular operating frequency. So as we also know that this gamma can be considered as a alpha plus j beta, where alpha is nothing but the attenuation constant while beta is nothing but the phase constant. So these equations are called a vector wave equations, and here for obtaining the solution of the E and H equations we have used the rectangular coordinate systems. So now let us try to solve the E and H equations. So for that let the rectangular component of the E and H satisfy the complex scalar wave equations or a Helmholtz equations. So I can express the above two equations as a del square sigma, that is equal to gamma square sigma. So this I will consider as a equation 1. So this is considered as a Helmholtz equations or a complex scalar wave equations. So this variable sigma, we are trying to find out this sigma. So this is what the solution of this complex scalar wave equations. So I can express this Helmholtz equations in a rectangular coordinate system as the partial differentiation del square sigma by del x square plus del square sigma by del y square plus del square sigma, that is divided by del z square, that is equal to gamma square sigma. So I will consider this as a equation 2. So you can clearly see that this is a linear and inhomogeneous partial differential equations. So we have to solve these equations. So by using the separation variable method, the solution of this equation number 2 can be written in the form of the sigma, that is nothing but equal to the capital X of X, capital Y of Y, and capital Z of Z. So I will consider this as a equation 3. So where this capital X of X is nothing but a function of X coordinates only. Same way this Y of Y is a function of Y coordinates only, and this Z of Z is a function of Z coordinate only. So this way I can say that this sigma is ultimately the solution of the three independent variable x of x, y of y, and z of z. So now, by substituting the equation earlier, my three equations, these equations into 2, and if I will try to solve and divide by the resultant this vector, this function, then I will get finally I will obtain from these equations, I will obtain these equations. So substituting the equation 3 into 2 and division by the resultant by the once again that equation 3, we will get 1 over x d square x by dx square plus 1 over y d square y by dy square plus 1 by z d square z over dz square, that is equal to gamma square. So here you can clearly indicate that each term is independent variable and must be equal to this constant. So here I can say that whole this term is equal to gamma square, whole this term is equal to gamma square, and whole this term z term is also equal to gamma square. So let me define now the new variable. So let I define the three terms kx square, ky square, and kz square respectively for these three differential equations. Then I can write that this is equal to minus kx square minus ky square minus kz square, that is equal to gamma square. So let me define now this new equation as a equation number 5. So here I can say that the general solution of this each differential equation, this d square x by dx square, can be considered as nothing but the minus kx square into x. Same way, the solution of these equations is nothing but the d square y by dy square, that is equal to ky square into capital Y. Same way, the solution of this is nothing but the d square z by dz square, that is equal to the minus kz square into z. So all these three differential equations, if it is then if I will find out the solution, then the solution of these these three equations will be in the form of the, because this expression is a double differential equation, differential equations, then obviously that for this kind of the double differential equations we have the solution like this. So where for this case we have a x equal to a sine in bracket kx into x plus b cos x cos kx into x. So this way now this variable capital X is a function of sine and cos, and some constant boundary conditions will use a and b. So this way we have a y equal to c sine ky into y plus d cos ky into y. Same way, the z can be expressed as the e sine kz into z plus f cos kz into z. So finally, the solution of the Helmholtz equations in a rectangular coordinate systems can be expressed as the sigma, that is nothing but equal to the multiplication of these x functions, y function, and the z functions. So we will get the a full term of this x, full term of this y, and full term of this z. So ultimately I am getting the sigma is nothing but the a sine kx into x plus b cos kx into x, c sine ky into y plus d cos ky into y multiplied by e sine kz into z plus f cos kz into z. So this way, this solution clearly indicates that the solution is completely dependent upon this boundary condition value a, b, c, d, e and f, and it is the function of the variable x, y and z. So depending upon the values of the x, y and z and the boundary conditions a, b, c, d, e, f, we will get the final solution of these Helmholtz equations. So now let us discuss the basic questions that when the wave which is going to be propagate in a rectangular waveguide. So there is a condition, and for that condition, first of all we have to define the new term, and that is nothing but considered as a propagation constant gamma g in the guide. So as we know that in our transmission line we have defined the propagation constant gamma, but here the propagation constant gamma g will be different than that intrinsic propagation constant. So if we will assume that the propagation of wave is in the positive z direction, then let we define now the new parameter, that is nothing but the propagation constant gamma g in the guide. So now we will define this gamma g as gamma g square, that is nothing but equal to gamma square plus kx square plus ky square. And now let me also add new term, that kc square. So now this kc square is nothing but equal to under root of the kx square plus ky square, and it is usually called as a cutoff wave number. So now I have introduced a new propagation constant gamma g in the guide, and which will be useful to prove that whether the wave is propagating in a guide or not. So let us see that three special cases. So as I mentioned that for the lossless case, for a lossless dielectric medium, we have a gamma square is nothing but the minus omega square into mu epsilon. Okay, but that we have already seen in our uniform plane wave case. But for this case, now the propagation constant is not gamma but gamma g. So this gamma g will become plus or minus under root of omega square mu epsilon minus kc square. So now as I mentioned, let us discuss the three cases when the actual wave is propagating in the guide. So for that case, let us case 1. So if there is a no wave propagating, if there will be no wave propagating in the guide, if and only if this omega c square mu epsilon, that will become equal to kc square. So here it is clearly indicating that if I operate such a operating frequency omega c, and if that is equal to become kc square, then obviously this term will become 0, and hence the propagation constant in the guide will become 0. So this is called a critical condition for a cutoff propagation. So the cutoff frequency for this case can be expressed as the omega c, that is nothing but equal to 1 over 2 pi under root of mu epsilon in multiply by the square root of kx square plus ky square. So this is the critical conditions. So this is the such a operating frequency at which if the signal is propagated, then there will be no wave propagating in the guide. So this is the first case from which we define the cutoff frequency. And we also know that for the waveguide case, it acts like a high pass filter, so there should be some minimum cutoff, there should be some frequency which should be cross over that cutoff frequency, then only the wave which is going to be propagated. So let us see the second case. So in a second case where the wave will propagating in the guide, if and only if the if and only if the omega square mu epsilon is greater than kc square. So as I mentioned that the here if the operating frequency must be above the cutoff frequency in order to propagate the wave in the guide. So here the gamma g will become plus or minus j beta g, and beta g we know that nothing but the it is nothing but the phase constant, but here the phase constant for particular guide, and hence it will become plus or minus j omega mu in bracket mu epsilon in bracket 1 minus fc over by f whole square, where fc is nothing but the cutoff frequency that we have defined in our previous case. So this way for any wave which if it has to be propagated inside the guide, then this omega square mu epsilon should be greater than kc square, or I can say the operating frequency must be above the cutoff frequency. So now let us see the third case. So in case 3, the wave will be attenuated if omega square mu epsilon is less than kc square, and in this case the propagation constant become plus or minus alpha g. So alpha g is nothing but the attenuation constant in the guide, and if I will put, then that will be also equal to become plus or minus omega square root of mu epsilon into square root of fc minus f whole square minus 1. So here you can clearly indicate that if the operating frequency is less than the cutoff frequency, wave will decay exponentially with respect to the minus alpha into z, and there will be no wave propagation as this propagation constant is a real quantity. Now there is no imaginary value or imaginary quantity present. So as we know that for the propagating wave in a propagation constant, the wave can only be propagated if and only if there will be some phase constant term, and if that phase constant or that j beta term is not present, it clearly indicates that the wave is going to be attenuated with respect to the minus alpha g into z. So this way we can say that the wave which can only be propagated inside the waveguide if the operating frequency is above the cutoff frequency. So this way we have seen the three cases for the propagation constant gamma g. Now let us finally conclude that now because of this, the solution of the Helmholtz equations in rectangular coordinate systems can be expressed as now only the x of x functions now only y of y functions, and because we know that wave is propagating in a z directions, and in that case the propagation constant is gamma g and the phase constant is beta g. So I have put here minus j beta g into z. So this way I can write that now the final sigma function, which is nothing but the solution of the Helmholtz equation, is a function of x of x, which is nothing but the function of sine and cosine with the variable x, and the y of y, and which is also nothing but the function of sine and cos, and with the variable y. So this function clearly indicates that the waveguide, the solution of that E and H field is completely based on the space variable x and space variable y. So how we choose this variable x, y, and how we choose the kx and ky cutoff number of that the x coordinate systems and the y coordinate systems, we will get the solution of that E and H field in the waveguide. So now we know that in waveguide there are different way to represent the field inside the guide, and based on that representation of that energy inside the guide, we will consider that as a mode of that energy. So we have seen that because in waveguide there is no center conductor, the TEM mode cannot exist. Here in waveguide case, we will always get TE mode or TM mode. So what is TE and what is TM mode? So we know that in case of the TE mode, we can define as as we have the total 6 scalar quantity in the waveguide, but if the Ez component become 0 and H of Z must exist, then that mode is considered as a TEMN mode. So please remember, whenever there is a Ez component is 0 inside the rectangular waveguide, I can say that TE mode is present. And if the HZ component is 0 and Ez is existed inside the rectangular waveguide, then that mode is considered as a TMMN mode, where this M and N actually indicates the number of the half cycles present over a x direction and over a y directions. So here mathematically I can write this cutoff number kx in the x direction is nothing but the m pi by a, and ky as a n pi by b. So this way this cutoff number is also clearly indicate it is the function of the mode m and n, and it is the function of the physical width and the height of that rectangular waveguide. So this way, in rectangular waveguide, in this class we have seen the solution of a Helmholtz equations in a rectangular coordinate system for a rectangular waveguide, and we have seen the 3 different conditions, and we have seen the TE and TM mode definitions. So thank you very much.